welcome to RF transceiver design course. In last class we have discussed about the noise and detailed analysis of noise we have done in the last two classes. We have also defined what are the types of noise and how you can find out the noise figure and how to measure the noise figure also we have discussed. So, detailed analysis of noise we have done, which will help you for any RF system design. Now, we are moving to the next important part for any RF circuit or transceiver design, that is a non-linearity. So, non-linearity plays a crucial role in RF design, and we will see all the types of non-linearity and we will try to derive the equation for the same. Non-linearity, there is a memoryless or a static system. So, what exactly it means? When your output does not depend on the past value of inputs. So, that is called a memoryless or a static system. So, here when we are talking about non-linearity, what is the condition for linearity, that also we need to we need to understand that what are the condition for linearity. So, the condition for linearity, let us say if I have a y1 t function, which is y1 is the output which is a function of a x1 t, then y2 t which is a function of x2 t. So, when I will multiply y1 with a e1, so the condition for linearity is a y1 t plus b y2 t is equal to f a x1 t plus f b x 2 t. So, what exactly it should follow the superposition theorem. If you are adding a two system with A or B and multiplying the gain A and B, when you try to add the both system, the output means your function output will also has a same addition and the multiplication. So, this is a condition for linearity. Now, the condition for memoryless system is if I have a function yt. So, if we try to discuss yt which is a f x of t, then the memoryless system, if there is a yt minus tau, then that is a function of x t minus tau. So, this system has a memory, then if you have a, it means it is not depend upon the means it is depend upon the present value, but if it has a memory, then it depends upon the past value also. So, there are many memoryless or a static system. Now, dynamic range and source of noise, when we try to see the dynamic range or source of noise, what generally if this is an amplifier and we try to increase the input power level. So, in this example what it says that I have a minus 100 dBm of input and I start increasing the power. So, as I start increasing the power, then if my output is equal to 10 P in, means the gain of the amplifier is a 10, then it is a linearly increasing with the gain of 10. So, as I increase whatever input power, it should follow the output, but in reality that is not possible for an active component. For passive devices, when we talk passive devices at microwave frequency, they all are linear. and another term is a deterministic, means you can prior you can know that what will be the output based on the function of input and the gain. But when we are talking about the transistor amplifiers, for that it is not true. After a certain point of time there is a compression, means the it will not follow the input, means it will not follow this equation, and your gain will start saturating. At the point at which your gain is 1 dB less than your ideal value, that point is also defined as a 1 dB compression point. So, there is a non-linearity associated with when we are dealing with the active component, and what are the type of non-linearity in RF system is there, we will try to understand. So, I just write it down, yt which is function of alpha naught plus alpha 1 xt plus alpha 2 x square t plus alpha 3 x cube t, and then it will go on. So, there is a any system which is a yt is depend upon the gain component alpha and the input, that is xt. So, here alpha is a time invariant. So, if alpha is a time variant, then that is also function of t, that is also function of t. So, what do we mean by time variance and time invariance? I will just want to give one example which will help you to understand that what do you what is meaning of time variant and time invariant. So, if there is a one input, that is a x to t, and there is one switch, the output is going to some resistor RL. Now, this switch has a input of x 1 t. So, x to t, if I will define x to t has certain amplitude a2 cos omega 2 t and x1 t which is equal to a1 cos omega 1 t. So, in this case what is happening, that your output is depend upon the x2 t and x1 t. Now, we will take a two case. If at this point output, so there is a two condition, if we consider x1 t as an input, if we consider x1 t as an input, then because the switch is switching on and off, so your output is varying with the time. So, then your system is a time variant. However, if my x2 t is as an input, so here there is a your output is also, and another point I just want to add here, that this there is a time there is a the output is non-linear. Now, when you also try to see the x2 t as an input, your output is a linear, but again there is a time variance. So, here if we try to draw the x1, x1, x2 and output, we will understand. So, let us say this is x1 and then this is x2. So, this is x1 t, this is x2 t and this is a output y t. So, now here what is happening, that when this switch is on, means the when it is more than 0. So, this is 0, then your x2 will be at the output. So, it will be roughly same. I will try to redraw. So, here what we are trying to do is we just try to replicate when there is a positive, when there is a negative it is 0, when there is a positive again it will follow. So, this as a same, then again it will follow the input. So, it is not as per the scale, but to have the understanding that if you consider the x1t as a input, let us say first case, then it is not at all linear output. This is non-linear because it is not following the equation that we have seen in the last slide. Now, here when you consider x to t, this is following the output when this is a positive. So, let us say if you have increased the your if you increase the amplitude of x to t, then there is a increase in amplitude of y t as well, but in the both the case it is a time variant. So, this kind of circuit we will see more in detail. This is mostly mixer, means starting of the mixer. When we discuss RF mixer, we will see more in detail. So, when you are considering time variant system, at that time your alpha is also function of t, but if you are using an amplifier, then you can consider it is a invariant, time invariant system. So, now we will try to get the function of x t. So, this is a memoryless also, memoryless or time invariant system. Now, if your x t, which is equal to a cos omega t. Now, before we will try to find out the y t, one more thing I just want to add, that is if you what kind of function can be possible if we are designing an amplifier. So, you can take an example as a common source amplifier. So, this is a RD and you can see this is a V in, this is common source amplifier, and V out. What is a V out? If I want to write a V out, that V out is given by VDD minus ID RD. If I again write the equation of ID, VDD minus half mu n C ox W by L VGS minus VT whole square into RT. So, in this case this is only first order term of ID equation. So, this ID can also be represented in a number of expansion, and it is a square, cube, all the terms where. So, generally this simulator will take care of this, but this is a we are considering the basic equation of ID, and we can already observe that if you try to correlate this YT alpha naught. So, VDD is nothing but alpha naught you can consider, and alpha, because your VGS square, then alpha 2 x square t. So, this is how your YT. So, here it is V out t. So, V out is a function of your VGS square. So, this function will go on because there are many nonlinear gains will be added when we consider the complete ID equation. So, we will try to solve this and find out what is a YT. We I will try to move delete. So, now we just try to put a cos omega t in this equation. So, what we will get is, if we do not consider the DC term, that is alpha 1 a cos omega t plus alpha 2 a square cos square omega t plus alpha 3 a cube cos cube omega t. I can again write it down, alpha 1 a cos omega t plus alpha 2 a square by 2 1 plus cos 2 omega t plus, we will differentiate this so that we will not confuse, plus alpha 3 a cube by 3 cos omega t plus cos 3 omega t. So, in this equation we are interested mostly on the a cos omega t, because other terms a square a cube. So, we are interested in cos omega t. So, what are the term is associated with the cos omega t that we will come by. So, first is there is a DC quantity alpha 2 a square by 2. So, this is a DC quantity, plus we can write it down alpha 1 a plus alpha 3 a cube by 3 alpha 3 a cube by, so this is alpha 3 a cube by 4 cos omega t, plus you can also write alpha 2 a square by 2 cos 2 omega t plus alpha 3 a cube by 4 cos 3 omega t. So, it has a many components. So, we will try to analyze this equation here, because we are considering cos cube t, it is 3 cos omega t cos 3 omega t by 4. So, we should consider divide by 4. So, both the case it is a divide by. So, here this is a nothing but, if I will try to change the color, this is a DC quantity. This is a because cos omega t is a fundamental harmonics. We are interested to understand what is the change in amplitude in the fundamental harmonic. So, this is nothing but a fundamental this is a second order and then this is a third order. So, this can be a third order. So, there are a first order term that is a fundamental harmonic, second order term that is alpha 2 a square 2 cos 2 omega 2 because it is a second harmonic, then this is a third order harmonics. So, let us say if your omega naught is 2.4 gigahertz, then your second harmonic is the twice of that 4.8 and third harmonic will be twice of that, and the amplitude will have the there is a change in the amplitude a cube. So, for this there is a square, for this there is a means a square by 2, for this there is a cube by 4. Now, if we try to sum up this, uh, if we consider even order harmonic here result from alpha j with even j vanishes if the system has a odd symmetry. So, let us say we already consider the example of the amplifier. If it is a differential amplifier, what will happen that xt, if it is xt is equal to x minus t, xt is equal to let us say xt which is, so here we can write it down. So, this is nothing but odd symmetry, and odd symmetry what will happen that when we try to square this signal, then the square of the minus x will also be the positive. So, we will not get the even harmonics because here in even harmonics there is a square term is coming, and that square will for both when we try to differentiate the signal, so that will be cancelled out. So, for differential circuits, that is why here it is written that even order harmonics result from alpha j. So, this is a alpha j alpha 2, that is a even order harmonics results from the even order harmonics result from the alpha j with even j vanishes if the system has a odd symmetry. So, if system has a odd symmetry, the example is a fully differential amplifier. For fully differential amplifier, you can consider it that even order harmonics will be reduced or eliminate. So, that is why we try to use the even order, we try to use the fully differential structure in the complete receiver chain, so that one of the harmonic component we can directly suppress. Another important notes that we can take from the last equation, that amplitude of the harmonic is proportional to the nth power of its amplitude. So, let us say if it is a second harmonic, then it is a square, if it is a third harmonic it is a cube, if it is fourth a fourth. So, the amplitude is proportional to the nth power of its amplitude, and the harmonic of the amplifier we can easily filter out at RF frequency, because I already given one example that if your f is a 2.4 gigahertz, then other frequency is lying very far, means other harmonics are lying very far. So, you can easily filter out the other harmonic component. So, now we are interested the component which is a fundamental harmonics. So, we need to consider the fundamental harmonic. Now, this fundamental harmonic has a two term, one is a alpha 1 and alpha 3. So, that is a alpha, first order alpha and a third order alpha. So, this here this alpha 1 and alpha 3 we can have a two behavior. If alpha 1 alpha 3 is greater than 0, that means there is a expansion. So, if it is a expansion behavior, then there is a alpha 1 alpha 3 is 0, but as far as amplifier is concerned, we mostly consider the compression where the alpha 1 alpha 3 is less than 0, because the amplifier is going to provide you the stable analysis or stable gain, and here alpha 1, the product of alpha 1 alpha 3 is less than 0. So, if the product of alpha 1 and alpha 3 is less than 0, then we can see that there is a compression in gain is occurring, and that compression in gain is occurring. So, after certain point of time, if your gain is compressed by 1 dB, then your ideal desired. So, this is a ideal and this is a actual. So, that 1 dB down it has that point is nothing but the 1 dB compression point. So, A 1 dB it can be considered as a 1 dB. So, we can try to solve the what is the A 1 dB and its equation with respect to alpha 1 and alpha 3. So, here your yt I am writing down again, let us your y t which is equal to alpha 1 a plus 3 alpha 3 a cube by 4 cos omega t. So, we are interested in fundamental harmonics and this is the amplitude of it. So, if I will consider, if I will take a out alpha 1 plus 3 by 4 alpha 3 a square cos omega t. So, here so we can get this equation. Now, what we try to find out is a 1 dB compression point. So, this amplitude here it is a cos omega t, because we have taken a cos omega t out. This is a desired signal that we want, and this is the amplitude which is added. So, if we want to find the 1 dB compression point, what we need to do is this alpha 1 plus 3 by 4 alpha 3 a in 1 dB, because we are finding out the amplitude input which is equal to 20 log of alpha 1 minus 1 dB. So, what exactly we want? This is a the gain, actual gain of the system is alpha 1. So, this is actual gain, but due to the non-linearity or harmonic distortion, there is a third order term is coming 3 by 4 alpha 3 a square, and that we try to subtract with the 1 dB. So, the point at which this is a 1 dB down means this is a actual system and this is the ideal one which is a 1 dB down. So, we are interested to find this point. So, now if you find out this equation, you will get, means if you try to work around and you convert log means anti-log, you will get a in 1 dB which is equal to 0.1 145 alpha 1 by alpha 3. So, your gain means your 1 dB compression point, this is a 1 dB compression point, is depend upon your fundamental gain alpha 1 and your third order alpha 3. So, in reality we do not want alpha 3 to exist, means ideally we do not want alpha 3 to exist, but in reality there is a some third order gain which is trying to reduce the gain of the actual system, and that point is nothing but a 1 dB compression point. So, this is very important uh, feature, important parameter of nonlinearity, which tells us the harmonic distortion, and we can quantify the gain compression for any system that we want to analyze. So, gain compression is important, and we need to find, we need to get the value of gain compression by finding out the gain, or plotting the asymptotic curve and finding out the 1 dB compression point. The typical value of this 1 dB compression point will be typically this value will be around minus 20 to 25 dB according to the minus 20 to minus 25 dB according to the requirement, and that can be improved based on the circuit design or by using some feedback topologies. So, thank you for today's class. We will discuss more in detail about the non-linearity. So, this is a harmonic distortion, and we try to find out the parameter of gain compression in this class. We will further discuss about the non-linearity in the next class. Thank you.